Welcome to ePathshala lecture series in computer science, and this is a course in cloud computing. In this module, we will talk about a special theorem and thereby NoSQL databases. So, today's learning objectives are first we will look at SQL database and what are the limitations, and we will look at the limitations in terms of the ACID properties that these SQL databases work with, and then we will move on to see what is CAP and what are the three properties or requirements in CAP, and a special theorem called Brewer's theorem, and thereby we will come to what is known as NoSQL data stores, followed by the summary. So, SQL databases are the most commonly used databases. This is the relational database that we have been using for quite some time now. MySQL, Oracle, you name any database, those are the relational data stores. Now, the property of these data stores is that they will store data in various tables, and these tables will be related to each other using their relationships across the tables, and it will be easy to retrieve data from these tables easily. So, these data stores have the property that they will be based in tables, and these tables can be joined, can be split, all sorts of work can be done on these tables. The query for retrieving data is based on structured query language or SQL, and therefore, these are called SQL databases. Now, database system, any database system, if it needs to support transaction, these systems must ensure that multiple transactions are supported. Databases must support some kind of interactions. They have to retrieve data, they have to store data, they have to update data, all these things. When it comes in the form of transactions, they have to support multiple such transactions, because each of these transactions, as we have seen in an earlier module, they are atomic, they have certain properties, and to follow these properties, things make very small steps, and unless we support multiple such transactions, the database cannot run efficiently. Therefore, the transactions will be interleaved with each other for faster completion, for better throughput. And what is the guarantee from the side of the database? The database has to guarantee that these transactions are interleaved in such a manner that there is a serial equivalence, which we have learned in our earlier module, that there has to be a serializability across all these transactions, and the database has to give that guarantee. And the transactions follow what is known as ACID property. Now, what is this ACID properties? ACID properties are four properties: atomic, consistent, isolated, and durable, and these ACID properties of transactions cannot be violated. Always the transaction has to follow ACID properties, and therefore, the databases that support the transactions must follow the ACID properties. What the databases typically do is they use locks. If I lock one transaction and then allow the other transaction to happen only after the earlier transaction has unlocked, then there is no problem of serializability. We have seen one such very popular locking mechanism called two-phase locking, where we used one phase to allow the locks and the other phase to release the locks, thereby ensuring that everything is perfectly done. So, the problem is it always possible to have interleaved transactions ensuring ACID properties? Let us look at RDBMS. This is let us consider a scenario where the database is distributed. So, we have a distributed database which means that different parts of the database will be located in different locations, and for better performance, what will also be done, as we have been seeing, that the data will be replicated. So, not only the parts of the databases will be in different locations, parts of the data will be same as in another location. In such case, in such a scenario, imagine we are trying to log a part of the database and then trying to access another part of the database, and when we have completed, we are releasing the log and allowing some other process or a transaction that is waiting in another location to start. So, for obvious reason, what will happen is the locking and unlocking mechanism across these data sites will really slow down the whole system. This is why we say that following ACID, atomicity or consistency, these are all very strong properties, and RDBMS or transaction supporting mechanisms allow or accept or follow very strong properties. Therefore, the problem is that RDBMS is not suitable for distributed environment. So, when there is a multi-node database solution, the advantage of having these distributed databases is that it will horizontally scale, it will spread itself to reach more customers, to reach more people. So, we can easily imagine data stores or applications, web based applications like say LinkedIn or Google or Netflix. They will have their data stores all across the globe, so that they can easily serve their customers. It is very important for them to have replicated data store all over the globe. So, what would be a requirement if strong properties are not a requirement? Then let us look at what would be the requirement for these web based applications. They have three major requirements. One, they need the ability to scale on demand. So, whenever it is required, they will scale out, whenever it is not required, they should be able to scale back in. The ability to have this scaling up and down at a high latency and low latency and high throughput, and these applications must be highly available. They should always be available. So, what about transactions? What about ACID properties? We really do not need ACID properties of or transactional supports anymore for these. So, the goals of these data stores are that all clients must see the same view even when there are updates. So, updates are going on, but there should be a similar view given, allowed to be seen by all the customers. That is the property of consistency. So, the data stores must be consistent. The second property is that any of their customers must be able to find the data or information at any point in time easily. So, that is the in spite of failure. So, that is the property of availability. So, the data stores must be available, and the third one is that in spite of failures, both these should happen in spite of failures, because we know that systems will fail. And when we say tolerance to partition, even when there is one system that has failed, that causes a partition in the environment. So, we call it a partition, and the system must be able to tolerate such partitions. So, when there is a physical network partition, or when there are multiple nodes that have failed, or when some disk has failed, for any such failures, the consistency and the availability property must hold on. So, the system must continue giving such information to the users. That is the requirement. So, these gaps, that is the consistency, availability and tolerance to partition, must be are the requirements for this. So, consistency, availability and tolerance to network partition, it is any partition for that matter. While these are desirable, is it possible to develop database systems which allow all the three properties? So, here comes the Brewer's theorem. The theorem says that of the three properties of shared data systems, consistency, availability and tolerance to network partitions, only two can be achieved at any given point in time. So, all three cannot be achieved, it is not possible. Brewer's theorem says that it is not possible to achieve all three. So, it is impossible. So, any combination of two of these properties can be must be chosen. So, what will decide which two will be chosen? That will be dependent on the technology that we are using, that will be dependent on the availability of what are the databases that are available, that will depend on the business application that the system is being used for. So, here is an explanation of the Brewer's theorem. These are the this is a triangle with three points having the three properties. If it is a CA, it is available and consistent, but network partition is not taken care of. If it is a CP, then it will be consistent in the presence of partition, but availability is not guaranteed. If it is an AP, then the availability is always guaranteed in spite of partition, but the consistency of the data, the correctness of the data is doubtful. So, here is the system which is consistent and available. So, we have the strong consistency. We can offer strong consistency for such systems, which means that it is always consistent, irrespective of how many updates are happening, the system is consistent. Data would be always available because it is a C and A. So, availability is there, but no network partition. That means no failures can be tolerated. In case of a very large system like cloud, we can easily understand that it is such a difficult proposition not to have any failures for that matter, but these systems work, CA systems work only in the absence of failures. Look at the AP systems where availability and tolerance to partition is are the two properties. So, these systems allow partitions, these systems allow failures, these systems are quite all right, they will be able to still deliver even if there are multiple failures. Then the databases will always keep answering. So, the availability ensures that whenever a user queries, whatever kind of errors that may have happened or failures that may have happened, the system will continue giving answers, but the data may not always be the correct data. The correct data in the sense how it is incorrect, the recent updates may not have been propagated yet by the system. And the third kind will be the CP systems, where again there will be a network partition or failures, whatever it is, and the system will not be able to always answer the queries of the users, but when it does answer, the answer will always be the most recent value that has been updated in the system. So, it is consistent, the data will be consistent, but the delivery of the data, delivery of the information is not guaranteed. So, if we tie all these together, what we obtain is that CAP provides the basic requirements of the system. ACID on the other hand is a set of rules that the database may choose to follow. In case they choose to follow, they have to give the guarantee that transactions will be handled in a certain fashion. And this Brewer theorem or the CAP theorem for that matter is a warning that strong properties like acid is not desirable in large systems because it will slow down the system. So, moving on, we need to, wherever we need to provide strong consistency and strong availability, we have to have the transactions in lockstep. We have to ensure that only one read or one write while the data is being read, while the data is being written, no read can be done, and vice versa. So, eventually this will reduce the overall speed of the process. So, the usual RDBMS is ACID compliant, it follows CA of CAP. So, what other options do we have? Is CA sufficient? CA is not sufficient because there will be network partitions. So, P is one option that we have to choose. So, in the presence of P, which is the failure option, what we can do, both C and A are not possible. So, which one we should choose will depend on the kind of application that we are developing. If our application can tolerate less availability and requires more consistency, then we should choose a CP system. If our application cannot tolerate lack of available data, but can tolerate a little bit of inconsistency, we should choose a CP, AP kind of environment. So, in a large distributed systems like cloud, what we should choose? Should we choose AP or should we choose CP? Again, it will be dependent on the application, but generally speaking, on an average, we sacrifice consistency and we move on to, we get the availability and network partitioning, which are the AP systems. What about HDFS? We have seen HDFS in Hadoop distributed file system in the last module. What does HDFS follow? Let us take the first property, availability. All the data is in the name node. So, the metadata is in the name node. The data will be in the data node, but all the metadata, and name node is a single point of failure. We also looked at that high availability option, whether although it is there, but it is not included in the basic. So, the secondary name node only checkpoints, it is really not a true complementary node for name node. So, therefore, it does not provide any real redundancy. So, Hadoop distributed file system is not always available. What about the consistency? All metadata is in the name node. Name node maintains all information, therefore, it is consistent. Further, typically the Hadoop, the data blocks are immutable, and since the blocks are immutable, again there is no problem of consistency. What about partition tolerance? There is a large number of redundancy in the HDFS, and therefore, it can easily tolerate a lot of failures. So, data node can be lost and some data stored. So, therefore, HDFS is a CP system, consistent and partition tolerant. What about ACID properties and Hadoop? Hadoop really does not follow ACID because it has no concept of transactions. So, finally, let us look at the problems of ACID. It is strong, ACID enforces strong properties. It will eventually slow down the system, and big systems like cloud cannot tolerate such slowing down, and it is not necessary to follow such restrictions. Weaker properties, weaker consistency properties are much successful. So, let us look at an alternative to ACID. The alternative to ACID is called a BASE. It stands for basically available soft state eventually consistent system. So, B and A are for basically available the system is available. Most of the times it is available, and somehow even if the subsystem is temporarily unavailable, it will not be felt in the, it will not go up to the client, the not availability. What about the data persistence? It is up to the user. So, it is called a soft state. So, the persistence of data is not looked at. What about consistency? It follows something called an eventual consistency. So, let us look at what is an eventual consistency rather than a stronger consistency. An eventual consistency says that, first of all, let us note that it is a weaker variety of consistency when we compare it with the strong consistency model. So, an object that is having multiple copies in different locations in an eventual consistency will be updated only in amount of propagation. What does it mean? That when we say that the data is updated, we guarantee that one location is updated and the other locations the updation will eventually be propagated. So, we do not assure in an eventual consistency assurance to in terms of all copies being updated is not given. The order, the other concept is that order in which the data is updated. So, if there are 3 or 4 updates, then the order in which these updates will be applied in data store 1 and data store 2 is not guaranteed in an eventually consistent data store. So, what do we do about that? We should create such updates that the order by which it is applied should not matter. So, eventual consistency follows that. So, once the object is updated, the distributed data, it is possible that the update will be sent to others only eventually, will be propagated eventually, and an update is successful if some of the stores are updated, not necessarily all. When a read happens after an update, there is no guarantee that the most recent update will be available to the user. There may or may not be the most recent update, it may be the earlier data, but eventually, typically this eventually is only a few milliseconds, eventually it will be available. So, base, cap and the new data store NoSQL. So, massive amount of data is being amassed by various systems today. We need to obtain models which can take care of such huge data stores, and ACID properties becomes very difficult to maintain. So, therefore, base concept is, base models are emerging. These are better for this kind of data that are being created, and these new data stores are called NoSQL data stores or NoSQL databases. So, before we go into the NoSQL database, let us quickly look at what is this, what is the requirement of these data stores. We have applications which are creating data. These data largely are not changed by the customers. The essential part of these applications are that the data should be accessed very quickly. Even when the data is changed, updated by customers, the guarantee is that some kind of data will be available, but either it will not be consistent or it will not be available, and it is perfectly fine to these applications. So, NoSQL are such data stores. The name is from the words not only SQL, which says that it may or may not support SQL queries. It supports all other query languages. One primary goal is that it will horizontally scale. It is easily scalable and horizontally scalable. So, partition tolerance is very strong. Therefore, even if so many parts of the network is partitioned, still these stores will continue However, either consistency or availability will be sacrificed, thereby Brewer's theorem is followed. So, this is becoming very popular. NoSQL databases are becoming very popular, where the ability is on the scalable storage. So, different data structures are used by different NoSQL databases. There is not only this table type of data stores that our relational databases were, although tables are also there in some kind, but the various models are created using different data structures. We will look only at a few of these. The first one is the key value store, where the idea is the data is represented using a key value pair. A key is the unique property in the system, and it will have many values associated with it. Consistency model will be eventual, even sometimes a serializability or the strong consistency is can be supported. The databases will support the ordering of keys. Typical example, very popular Oracle NoSQL database, Redis, LevelDB, etc. Document store, here the central concept is the document, and these documents encapsulate all the information in standard formats. The document format supported XML, YAML, JSON, BSON, etc. The documents are addressed using a key, and this key is again unique. Therefore, search will be based on the keys, and also some APIs will be, or query languages will be offered to retrieve documents based on contents as well. MongoDB, CouchDB, Riak are examples of document store. Column oriented store actually supports the tables. However, the tables are column wise and not row wise. Row wise were the relational databases, column oriented are column wise, and therefore table join, which is a very strong point for relational database, is not possible in these column oriented data stores. But the aggregation, the aggregation of such data is easy. Bigtable, Cassandra, HBase are examples. Graph has become a very important part of how we represent our data. We see in all social networking there are graphs. We talk of Facebook, we talk of Instagram, all these are graph represented. So, using graph as a data structure to store data is very important, and a large number of graph based models are available in NoSQL data stores. All these Google Maps, any network topology, all these are part of it. Neo.js4, Giraffe, Titan are examples. Now, when we look at these NoSQL systems, where do they stand in terms of CAP and Brewer's theorem? All these have to follow Brewer's theorem in the sense that they cannot be having all three properties. So, we start with our first data model, which is the relational model. We know that relational model is a CA model. Next, we see the key value pairs. Some of the key value pairs are CP, Voldemort, and some are AP like Memcached-DB, Redis, etc. Then we look at column oriented data stores. One column oriented data store is actually a CA model. Column oriented are table oriented, so therefore, it is possible that they support very strong consistency. So, this is Vertica is a CA model. Other column oriented are Cassandra, Bigtable, HBase, they are either CP or AP models, and document oriented models are SimpleDB, CouchDB, Riak. These are CP, whereas MongoDB is an AP model. So, finally, SQL is a very good option. Why SQL is also a very good option, and are we ready to sacrifice SQL for the new kind of data stores? The answer is no. There are quite a few reasons for it. The first being that we have still a large amount of data stores which are bound in our relational tables. That is one. The second is there are applications where the ACID properties and transactions are a must. If we take a bank application, there is no way that we can sacrifice our consistency and availability. So, therefore, strong properties also are required for many applications. On the other hand, large distributed applications are aplenty in the world today, and they cannot have the SQL kind of data stores. So, NoSQL is great, but it does not work for all kinds of models. SQL data stores are also great in their own ways. Again, they are not suitable for the newer kind of applications that are web based applications that are developing. So, what do? We take a combination of SQL and NoSQL database. We use both. We store our such data which requires stronger properties, we store such data which does not require stronger properties in our NoSQL and strong properties in the SQL data stores, and manage with these. So, to summarize this module, we have the SQL databases. We looked at SQL databases and ACID properties, and then we saw that ACID properties, guaranteeing ACID properties actually affect adversely to some applications which really do not care about giving strong consistency and availability all the time. They can sacrifice one on the requirement of the other. And we looked at HDFS, and we saw that HDFS does not have the availability, but has the CP properties. We looked at an alternative to ACID which is abbreviated as BASE, and these systems support what is known as eventual consistency. We looked at eventually consistent data stores. Many of these are actually eventually consistent, others are not available, not always available data stores, which are the NoSQL data stores. This completes our discussion on cloud data storage. Since data storage is a very important part of cloud, we have been discussing data store for the last few modules. Now, the next class we will look at another very important criteria in cloud, which is the cloud networking. These are our references. Thank you.